Hi everybody, this is our seventh laboratory experiment or the seventh simulation that we are conducting for our college physics course. Then today's lab is about torques, equilibrium and center of gravity. So as always, we are going to do some kind of improvised version of our physical lab. So since we cannot do the physical lab, then the simulation is going to be somehow an improvised version of like what we normally do in a lab. Okay, so just simply follow the procedure that I'm carrying out, and then you'll try to figure out and do a similar information or a similar kind of work on your lab. So on your lab, what we have here is like different cases of trying to balance a given meter stick kind of thing. So pretty much we'll try to follow a similar procedure, and we're going to do like something similar to case 1, something similar to case 2A, case 2B, and case 3. So now I'm going to go ahead and then give you some introduction about the lab and the theoretical background. So the first thing is what we need to know is like what's torque. Okay. So the first thing that we need to know about torque, which is a physical quantity, torque is the tendency of force to rotate something, okay? Or to rotate just an object. So like, what is the effect of force like in terms of trying to rotate a given object? That is what torque is. And torque is represented by Greek letter tau, okay? So this is the normal representation of torque in physics. And when we come to the definition of tau or torque is defined as like torque is equivalent to the perpendicular distance from the line of action of the force multiplied by the amount of force that you have. Okay, so for instance, if you look at like just a door, for instance, like just let's say here's a door, and here's like, let's say this is the hinge of the door, and then let's say here you have the handle. Okay, so you're seeing it from the top. So for instance, like when you are closing or opening the door, what do? Normally you just push it right here on the handle. Okay, then that is what the force is. Okay, and then the line of action of the force, so the force is acting in this direction, and when you apply the force on the door, what happens to the door? So this is just pretty much a top view of the door, okay, when you see it from the top view. Okay, that means like it's going to look like, so this is the thickness of the door. Okay, so here's where the hinges are. When you see it from the top, it's going to look at like just dots, right? Most hinges, they look like some kind of a big bolt or some kind of nail. So when you see it from the top, it's just like a dot. So the lever arm, and then when you apply the force, what happens is like the door will rotate about the hinge, and then it's going to open, right? So the distance from where you have the hinge, that is where the force is going to open the door or rotate it, okay, to the line of action or to where the force is being applied. Then that is what is torque is. Okay, so here what you're seeing are like this. I'm representing it. It means the perpendicular distance. Okay, so this means like perpendicular distance from point of rotation. This is the general definition, okay, because you don't have hinge all the time. Point of rotation to the line of action for the force. the line of action of the force. Then we already said tau is torque, and then of course F is force. And then most of the time, if we're using for following SI units, then force is in Newton, and our perpendicular or distant, that is in meter. Okay, so as a result, the SI unit of torque is automatically, it's going to be Newton meter, right? And this Newton meter is not something similar to what we saw for energy. What we defined in energy is like Newton times meter is equivalent to 1 joule. We did say that like when we talked about energy and work. But in case of torque, this Newton meter doesn't have any special name. We just simply measure this, whatever amount of torque you have in Newton meter. Okay, so that's the SI unit of it. And then keep in mind, torque is a vector quantity. Okay, torque is a vector quantity. And then something like, for instance, it's a vector quantity. If it is a vector quantity, then how do we determine its direction? Then the direction of a torque is mostly determined in terms of using the right hand rule and so on and so forth. But we're not going to go to the details of that because it may involve some kind of cross product of vectors that is not part of really this particular course. But in general, what we do for our own case, what we do is like, if a torque is acting in the counterclockwise direction, then it's considered as a positive torque. And if the torque is trying to open something in the clockwise direction, then that torque is considered as a negative. Okay, so now since we already defined torque, then what is the importance of torque in our today's experiment? So I'm sure that most of you might have played Seesaw game when you were younger. It's fine if you are playing it now as well. So what would happen is, like, for instance, if you take the seesaw is something balanced like this. I mean, it's supposedly just something like this. It's just like, consider this is a horizontal line. So what is going to happen is, like, for instance, if two people are playing a seesaw, let's say one person is, let's say he is 50 kilograms, and he's sitting at a distance of, let's say, 2 meters. And the other person who's playing on this same seesaw is, let's imagine, it's like 100 kilogram. Okay. So if you try to ask yourself, and then, like, let's imagine that they are planning to have this thing and to keep it balanced. That means, like, it's not either tipping to the counterclockwise direction or tipping to the clockwise direction, just to keep it. Then what do they do? What do they need to do is, like, they have to balance the torque. That means if this is mass 1 and if this person is mass 2, and if someone asks you, like, where should this mass 2 be seated so that the two will achieve equilibrium? Equilibrium means no rotation. Okay, so most of our today's lab is going to revolve around balancing a given meter stick. A meter stick means some kind of a ruler or something like that. Okay, so what is going to happen is, like, here the first thing that what you need to do is the net equilibrium means the net torque that is acting on the given system has to be 0. Okay, that means, as we said it, like, torque counterclockwise is positive plus torque clockwise, which is negative, is equivalent to 0. That means if you take the counterclockwise or the clockwise torque to the other side of the equation, what you will have is torque in the counterclockwise direction is equivalent to torque in the clockwise direction. That's the only time that you will be able to achieve equilibrium. So now, in this particular simple example that I'm trying to solve for you, is now which one is going to create counterclockwise torque. So if you look at it here, then mass 1 is going to create counterclockwise torque. So how do you find counterclockwise torque? Counterclockwise torque, as we said it, the force or the lever arm multiplied by the perpendicular lever arm. Okay, so the perpendicular lever arm, the force, but you may say like, okay, which force? So let's put force 1 and R1. So R1 is this, is what R1 is. R2 is unknown and we represented it as X. Okay, then how do you find F1? F1 is just simply the weight of person 1, right? Because F1 is acting in this direction. Okay, so that's what your F1 is. And then of course, similarly, your F2 is going to be the weight of the second person. You may say like, how about the plank or the wood or the metal or the seesaw itself, its weight? We are going to assume it's uniform, okay? And at the same time, like it is just hinged at exactly at midpoint. Okay, uniform means its mass is just uniformly distributed throughout the plank equally. So weight 1 will automatically be, how much will it be? It's going to be mass 1 times gravity. You may approximate gravity as 9.8, or you can just simply approximate it as 10. Okay, so we can approximate it as 10. So as a result, your F1 is going to be mass 1, as we said it, like 50 kilogram multiplied by 10 meters per second square. That's going to give you 500 Newton, right? So your F1 is 500 Newton. And R1, we already said it, it's 2 meters. So therefore, torque in the clockwise direction is going to be equal to 500 times 2. That will give you 1000 Newton meter. Okay, then now what we're trying to do here is to balance those two. So therefore we need to find torque clockwise, okay, or just simply you can represent it as CC. So torque clockwise is going to be F2 multiplied by R perpendicular for 2. So F2 is equal to the weight of the second person on the other side. That is mass 2 times gravity. Mass 2 is 100 kilograms and gravity we are using 10 meters per second square for simplicity. So as a result, your F2 is going to be 1000 Newton. But your R2, we called it A. So therefore, your torque clockwise is going to be F2, which is 1000 multiplied by X. X is what we have R2. So under the condition of equilibrium, especially like we call it the second condition of equilibrium, okay, so the sum of all the torques must be equal. Then to achieve equilibrium means balanced. So equilibrium will only be achieved when the two torque are the same, right? So as we said it, torque counterclockwise equals torque clockwise. Now torque counterclockwise, which is already calculated as this value, right? Remember? So then 1000 equals torque clockwise is what we have here, equal to 1000 X. Then to isolate X, what do you need to do? Divide both sides by 1000. By 1000. Why 1000? Because the number right next to x is 1000. So therefore x will be 1000 over 1000, which is 1 meter. Since we kept everything in SI units, so therefore our x value is going to be 1 meter. So if you look at here, intuitively probably when you played Seesaw, what you would notice is, like, for instance, the lighter person has to be seated further from the fulcrum if he's trying to play with a heavier person, right? So just intuitively, like if you are a heavier person, if you are trying to play with somebody who's lighter than you, then what would you do? Then you would sit a little closer to the fulcrum. So in general, like, the act of balancing can only be achieved in case of a seesaw-like experiment is like if the torque on the right hand side and the torque on the left hand side are the same. This is the theoretical background pretty much. Then what we are expected to do for the experiments is the following. So I'm going to send you like the lab simulation. So in this case, what we're going to use is the Fate Colorado simulator. Okay. So now I already prepared a table, something exactly similar to this one, except that like it doesn't have the x's. Okay. So we are not going to use the values of the x's because just our data set just directly gives us the r values. Okay, so then we're not going to focus on the x values. We'll just simply directly find the r values. As we say, the r values are the lever arm. That means the distance from the mass to the fulcrum or to the support. Okay, so for the first case, that what I want you to do is I want you to look at like my table, which is very similar to what we have there. Then the first step is you look at your data. What I want you to do is I want you to balance a 5 kilogram and a 10 kilogram. Okay, so for this one, what you would be expected to do is like you will open this, and then of course you put it like that, and then just put it on a balance side, and then put in if you want, you can have a level. A level means like just to see how balanced your thing is. So since we are assuming this plank is uniform, then it's just like balances itself if you are not adding any kind of mass. So keep in mind, make sure that you are going to click on the lab, okay, not the introduction part or not to the game part. Then let's put on a ruler. Okay, so in this particular case, now what I want you to do is take a 5 kilogram and put it somewhere on the left hand side, and then take a 10 kilogram and then put it on the right hand side, and then just play around. I don't know where you want to put it, just it's up to you, but make sure that like you balance those two masses. Okay, and then you must show your work. That means like what's going to happen is like what you're going to do is you'll have the 5 kilogram mass. So let's say fulcrum is here, and then you put the 5 kilogram mass on this side. I don't know where you want to put it. It's up to you. You can put it at 1 meter. You can put it at whatever mass or distance this thing gives you. You can put it at 2 meter. It's up to you. Let's say that. Okay. So but this is, make sure that this is the 5 kilogram. Okay. And then what will you do? And then you take like the 10 kilogram somewhere. I don't know. Then 10 kilogram. And then you balance it using the experiment or the simulator. Okay. And then at the same time, then you must show your work at the way I just showed you. What will you do is like you will find the torque in the counterclockwise direction that is created by force 1 times lever arm 1. Okay, that is the perpendicular distance. So in this particular case, how do you find F1? F1 will be the weight. So 1, or the weight of the 5 kilogram mass, the one that is on the left. How do you find it? It's just simply 5 kilogram times 10 meters per second squared. Okay, 10 is like gravity. Just for simplicity, I'm using 10. You can use 10. If you use 9.8, that's fine as well. Okay, so therefore you'll have 50 Newton here. Okay, so therefore you find CCW as 50 times any distance, whatever you choose. For instance, in this particular case, I chose 2. So what would be this value? This is going to be 100 Newton meter. Then similarly, you find the torque in the clockwise direction. That means created by this guy. Okay, see, this mass, the 10 kilogram, is tending to rotate this object in this direction. That's why we call it like clockwise. So similarly for that, it's going to be F2 times R2. R2 is X in this case. So your F2 is going to be the weight of the second object, which is 10 kilogram times 10 gravity. So therefore that's going to be 100 kilogram meter per second squared, or known as Newton. Then what do? Then you will do like 100 Newton times the lever arm. You don't know it. You can call it X, you can call it Y, doesn't matter. Then since the two are balanced, then you just equate the two and then you find the value of X. You do the same thing, like, so therefore, but in your report, like what you have to do is you need to show me like how whether you get the things balanced or not. Okay, so for instance, when it's balanced, you will see something like this, and the levels turn to green. Those are the levels. Then but make sure that like you do the calculation, and then you must show that like the 10 kilogram is located at a given point. Okay, so that's for the first part. That's what you will do. R, you choose your own. I chose 2, for instance, as an example. You choose 1.5, you can choose 2, you can choose 3, I don't mind. But make sure that like you do the calculation for torque counterclockwise the way I did it. Please make sure that you also calculate torque for the counterclockwise version. And then after that, like you find the percent difference between the two, this and this. Okay. Most likely it's going to be 0 because this is a computer simulation. Now for the second part, what you need to do is I want you to take 10 kilogram left. When I put a parenthesis left, what I meant is like put that mass on the left hand side. Okay, so take 10 kilogram and put it on the left, and then take a 15 and a 5, put both of them on the right. Again, this is just a matter of your own choice. Just choose a location for the 10, choose a location for the 15, choose a location for the 5, then find the clockwise and counterclockwise torques. Okay, so in this case, what you need to remember is like you have 2 forces on the right hand side. So therefore, like what you're trying to do is, in this particular case, you will be using a 10 kilogram mass over here, and on this side you will be using a 15 kilogram and a 5 kilogram. This is an example. I don't know, the 5 kilogram maybe in front of maybe it's here, it can be in front of the 15 kilogram or vice versa. I'm just giving you an example. So what makes this calculation different from the previous one? What's going to happen is like now, when you find the counterclockwise torque, you only have 1 force. But when you are calculating the clockwise torque, you're going to have 2 forces. That means 2 lever arms. Then you will have, like, for instance, this is lever arm 1. This is lever arm 2. Then lever arm 3 is going to be this distance. Then you use this system. And then when you are finding torque clockwise, counterclockwise, it's going to be just simply F1 times R1. But when you are finding the clockwise torque, it's going to be F2 times R2 plus, because you have two forces, F3 times R3. Sorry, I call this R2, but it is R3. Okay? Okay. Because those two forces are, both of them are tending to rotate this thing in the clockwise direction. That's why we are adding them. All right? So that's what the second part of the experiment is. The third part of the experiment, I already gave you where to put the masses. Okay, that means you take the 15 kilogram mass and then put it at 2 meters. You take the 20 kilogram mass, put it at 1 meter, and then put 5 somewhere. Okay, somewhere, and then put it somewhere and then find its location. So that means, where is it located? That's your measured one. From the simulation, you find it, and then from a calculation, you do a mathematical calculation as I showed you in the previous examples, and then find R3. Okay? So what you're going to do is the 15, the 20, and the 5. So what's going to happen is you take the 15 kilogram and then put it, so put your rulers, right? It says put it at 2. And then take a 20 kilogram and then put it at 1. Now, at the 5 kilogram, and I don't know where, just put it somewhere so that like the two items are balanced. Okay? All right? So, I don't know, maybe here, maybe here, maybe front of it, I don't know, but just find the location of the 5 kilogram from the simulation, and at the same time find the location of the 5 kilogram using the equilibrium equation. Okay, so make sure that like you're not expected to move the 15 and the 20 kilogram masses. They are already fixed. The locations are given, unlike the previous cases. In the previous cases, it's just like it's choice. Okay. Then the last and the fun part is you need to find there are mysterious masses in the simulation. Mass A, mass B, mass C, mass D. Those masses are not known. Okay. So what you're expected to do is like reset the whole system. And then put it here. And then rulers are good and levels are good if you want. You can also show the forces sometimes. It's up to you. Then now what you will do is use any mass. Like for instance, the mysterious masses are here. So make sure that like you click here until you see mass A, mass B, mass C. Okay. We're not going to go to the other ones. Then take mass A and then put it here. I don't know, put it here, or you can put it on the other side if you wish. Okay, and then use a known mass of your choice, okay, to balance it. Okay, so put it here. For instance, it's not flipping. Put it there. It's not flipping. There. Put it there. Maybe the 10 kilogram mass is too small. Maybe you may assume that's too small, or maybe put this guy like a little to the front until you find like some kind of balancing. Based on that, you do a calculation and then you show like what is the mass of object A. Okay, using this balanced system. You do a similar trick to find the mass of B. You may use a different mass in this case. Okay, you may use or an additional mass, or just simply use a bigger mass, and then try to balance this. And as soon as it balances, you take your data, That means you know where the 20 is located, you know where B is located, and then by combining those two information, the torque on the left created by the 20 kilogram mass must be equal to the torque created by the weight of B. You know, the location of B is known, the unknown part is only the mass, then based on that you can find it, okay? So you will do the same thing for C and D, and then you will show, you will show your calculation. So make sure that like over here, you must show a balanced diagram. So for each of them, I would like to see a diagram. What do you mean by a diagram? Like, you know, show me a balanced diagram. Like for instance, in the previous cases, like, you know, take a screenshot or something like that whenever you achieve a balance. And you know, take a screenshot and then send it and attach it as your lab report. Okay, so you know, you just play that with the 20 or with the 15. Or you know, something like that. And as soon as you get a balance, then you know, you take a picture. This is not balanced, of course. Don't take the screen picture of this. Then you take a picture, screenshot, and then attach it as your part of lab report. Okay. As always, this is fun. All right. Thank you. Then see you next time.